Great, okay, so we have limited time. I have some notebooks and I have some slides. It's the end of the day, so I figure you're probably exhausted. You don't really want to think through how do I code this up in a notebook? So unless there are any objections, I might just scroll through the notebook and sort of tell you what's going on. Your brains are all fried, I'm sure. Mine is too. Okay, great. Intro to causal inference. Causal inference is a really, it's very theory heavy and math heavy and philosophical topic. So I'm gonna try to make it as practical and down to earth as possible so you can leave here and immediately learn more if you want. Or leave here and say, this really isn't for me. So I'm gonna go learn something else. That's cool too. So I'm hoping by the end of the session, you'll have a good sense for what are the problems with analyzing observational data, because there are many. Understanding the various types of causal relationships you could have in nature. Understanding how statistical analysis, causal inference, and experimentation, or A/B testing, relate to each other and their various strengths. And then hopefully you'll have that foundational knowledge to kind of go forth and do something yourself. I think you can after this. But to begin with, I think this is a useful frame for thinking about causal inference. Way back in the day meaning 2020, there was some suggestion that vitamin D was associated with severity of COVID symptoms. People thought if you really mega dosed up on vitamin D, you might have less severe symptoms if you caught COVID. We're not really sure, but that was the thing going around. And if you think about how in an ideal universe where you have all the power you need, you can sort of shape reality and stuff, if you wanted to understand if that was true or not, you would take someone, you would sort of note their daily habits, what they do, where they work, what they eat. You would note that in early 2020, they start megadosing on vitamin D. They live their life, they stay isolated, they occasionally meet a friend outside, blah, blah, blah. They get COVID with mild symptoms in mid-2020. Okay, you can't really tell much from that though, right? It could be a whole host of reasons why they only got minor COVID. What we could do if we had all this power in the universe is examine something called a counterfactual scenario. The word counterfactual comes from philosophy and history. It's a term that's used in those disciplines. It just means what we don't observe in reality. It's counter to fact. And in this alternative reality, you could create exactly the same person who never takes vitamin D, but we hold constant every other aspect of their being, who they are friends with, what they eat, where they work, etc. And we followed them forward and we could see what happens. And then you would have a real understanding of, for this individual at least, what is the effect of vitamin D supplementation. Now, obviously, we can't do that. That's like black magic. But what we can do is, and our best attempt at this, is rolling out A/B tests or randomized controlled trials, or whatever you want to call it, experiments, where we take a group of treated individuals and a group of control individuals, and we sort of roll forward in time and see what happens. In one group, we have some sort of intervention. Maybe the treatment group takes high-dose vitamin D, the other one doesn't. They take a sugar pill or something, some placebo, and then we see what happens at the end of the day. The problem is experiments aren't always going to be there for us. Experiments are costly. They take infrastructure if you're in the tech world. Sometimes they're not ethical. So I'm an epidemiologist by training. I used to study lead exposure in children, and I can't dose pregnant mothers with lead. That's highly unethical, right? Sure, I could do something else interesting, like maybe I could roll out remediation efforts to various households and see if there are positive impacts to that, and sort of backwards infer that lead has an effect there, but there are problems with that too. They're also just not feasible. If econometricians want to know if household income levels in neighborhoods are associated with violent crime, we can't randomly swap homes, and so we have a very homogeneous high-income group and a mixed-income group and see how violence plays out. There are big problems with that, right? So the whole point of this talk is to introduce this category called causal inference. Causal inference is sort of this in-between ground, or that's how I like to think of it, between the highly idealized randomized experiments on the right there, which are difficult to roll out sometimes, but you can make really strong causal claims in them, to, on the other end of the spectrum, just getting a data set of something you observed in real life and running correlations on it. There are problems with that. We'll go through that in a little bit. So causal inference is this nice sort of middle ground here. And in a lot of organizations like my own, where we can't readily do experiments because we work with a certain type of patient data and it's just difficult to do that, we rely on causal inference quite a bit, and we try to beef up on that skill set. So that's what we're focusing on. I would recommend going forward, you think of causal inference as sort of in the same bucket as experimentation. It's not really, we use ML and causal inference, but it's not like another ML tool. It's more like along the lines of A/B testing, essentially, in that same bucket. But to help spell that out even more, here are a set of very typical causal inference type questions, research questions. And below that are typical ML questions. So questions like, how does improving neighborhood income inequality reduce neighborhood crime rates? Or how does increasing or decreasing the price of a product impact demand? In the causal inference bucket, all these questions involve some intervention or some treatment or doing some action, right? In the ML questions, there isn't that action necessarily. It's just, how can I cluster stuff? How can I predict whether this tweet is a nice one or a bad one? How can I predict whether patients will get diabetes or not in the future? So with causal inference, there's always this notion of an action, an intervention, a treatment, a policy. There are tons of names for it, but basically it means you doing something, and we want to see the impact of it. Does that make sense? Because that's kind of critical, actually. So, okay, cool. Can you raise your hands if you're familiar with graphs? Because I can just skip over this if everyone is. Oh, wow, a lot of people are. Okay. Really quickly then, I'll just speed through this because there's a lot of stuff here. Causal graphs are a way of representing data and causal relationships between them. There's a lot of really complicated causal inference approaches and sort of theory around graphs. We're not going to do that at all because it's confusing to people, I find. But just to kind of like get a baseline foundation out there, you can think of A, B, C, D, and E as representing variables or like entities or concepts, right? And what the arrows indicate is A causes E. It's a causal relationship. B causes E. C and D, that double-headed arrow there, can mean one of two things. It can mean it's sort of unspecified, like we don't know, they're correlated, or it could be bidirectional causation, like depression and physical activity are bidirectionally causal. Like if you're depressed, you're less likely to exercise. If you don't exercise, you are more likely to be depressed. It sort of goes back and forth. And so that's essentially how to interpret a causal graph. It's a really useful way of describing causal relationships, which we'll do in like 2 minutes. Usually this exercise is it's a car insurance one I do for folks that are sort of newer to causal graphs, but I think almost everyone raised their hand, so you get the idea. So I'm going to speed ahead. So taking this idea of a causal graph, we're going to look at 3 critical types of causal relationships in the world that you'll be considering all the time in your work. Critical ones. So the first one, and this will lead into the first exercise, by the way. The first one is something called a confounder. That's really annoying how it formatted the T there like that. The way you can think of a confounder is this. So you have some treatment, right? Some action you want to take, and you have some outcome. Analogous in some ways to like an ML problem. You have predictors and you have the thing you're predicting. So you have some action and you have some outcome, and you want to understand this relationship. A confounder is a third variable that causes both. Doesn't seem like that big of a deal, but it actually is. It's really important. A confounder will essentially induce bias in the relationship between your treatment and your outcome. And so if you don't account for confounders in your causal inference analysis, your results will be biased. And so very typical example here, there's actually a really well-known, commonly discussed correlation between coffee and lung cancer in the epidemiology community. It doesn't actually exist. There's no causal relationship between them, but if you're given a data set of like people's coffee consumption and whether they got cancer down the road, you will oftentimes tend to see a strong relationship. It doesn't exist. There's no causal relationship there, but smoking is causally related to coffee consumption. That's actually like a real psychological fact related to dopamine. And smoking causes lung cancer. And so smoking acts as a confounder between these two. And so anytime I want to understand the true causal relationship, if there is one, between coffee and lung cancer, if I don't account for smoking, I'm going to be way off base. It's going to induce a spurious relationship between coffee and lung cancer. This is called confounding. It's a bad thing. You want to prevent it. Confounding can do all sorts of interesting, awful things. It can cause positive associations. It can cause negative associations when they don't exist. Ideally, in some model that you build, you want to control for it. We'll get into that a little later. And a situation where you don't fully control for confounding results in something called residual confounding, like leftover, unattended to confounding, which is not great. Yeah, we can skip that. So to make it more real, I think, let's say like you're a mayor of a city with a lot of violent crime. And you have a team of analysts that are running around the clock to like figure out stuff for you, answer questions, et cetera. And they come to you and they say, we have this huge data set of observational data, and we found a really significant association between ice cream consumption and violent crime. And maybe you should do something about this. Obviously, like the naive approach would be like, well, there's a correlation, so there must be a story there, right? But there isn't one. The truth is, there's confounding going on here by warm weather. In the summertime, there tends to be more violent crime because there's more opportunity for it. And ice cream sales are higher in the summer than they are in the winter. And so that's what's going on here. It's inducing this relationship by causing both the treatment and the outcome. And so my potential treatment of tinkering with ice cream sales isn't going to do anything in real life because there's this confounding going on. If we somehow find a way to control for this confounding variable, you can begin to understand the true relationship, if there is one at all, between ice cream and the outcome. And maybe if there is one, then maybe ice cream sales, working on that as some sort of treatment or policy, would have some good impact for you, but I don't think it would. So we're going to get into like how you can control for things in quotes in a little bit, but let's not get too ahead of ourselves. We control for things in two ways. The first, like simple, naive way is to simply condition on something. Like stratify on it, essentially. So if I have a data set of, I guess back in this case here, I'll go back to this. If I restrict my data set so I only have observations in the summertime, this summer variable is no longer going to exert an effect on this relationship. There's no variability to it. It doesn't vary between 1 and 0, 1, 2, 3, 4, or whatever. So if you hold constant this confounder, it's very simple, it's very naive. It'll shrink your sample size quite a bit, but it will work to control for things. That's the simple, naive way. Two, which we're going to go into a little bit later, is to use a model. So just keep that in mind. All right, so we talked about confounders, right? You always want to control for confounders. You want to identify them using domain knowledge and empirical data. The next two relationships are things you don't want to touch. Like ever. Don't throw them in the model, don't control for them. Just know what they are, recognize them in your data using domain knowledge, and then just sort of like leave them be. The first one is known as a collider. So again, God, I hate that. You have this treatment causing an outcome. Collider looks like a confounder, but the arrows are different. So now you see the arrows are flipped. These two things cause the collider. If you control for that collider, you will bias any association between smoking and lung cancer. And this is a reason why, if you're doing causal inference, it's actually a really bad idea to throw a bunch of variables into a model without actually like thinking through the sort of domain reasons for why they're there. So in this example, again, like think of smoking as an intervention or something you want to act on. Like we could reduce smoking in a population or have some tax on smoking, and lung cancer is the outcome. Both smoking and lung cancer cause a large number of sick days to be taken in populations, right? Because if you smoke, it causes like health problems, immediate health problems sometimes. And lung cancer will necessarily result in like number of sick days being taken being higher. And so if you have a data set with smoking and lung cancer and number of sick days taken, you would never want to control for that collider, that red thing on the top. That would induce collider bias, which could either be positive or negative in direction, but it's going to essentially hurt your relationship of interest, the assessment of it. Third thing that, again, you don't want to touch, just be aware that it exists and kind of recognize it, identify it in your data is something known as a mediator. A mediator is, so again, you have a treatment, you have an outcome. A mediator sits in between them. One causes the other, which leads to the other. So what do you think would happen if we killed the mediator in this? If we somehow found a way to control for it, and let's say there really is a causal relationship between treatment and outcome, and I take out that pathway in the middle, I think it would result in us estimating no association or causal relationship between the two, right? Because I've taken out the pathway. That's what happens. If you control for a mediator, it'll completely nullify any causal relationship between treatment and outcome. So if I were to have some sort of data set that had smoking, lung cancer down the line, and clinical signs of lung damage, like sort of pre-cancerous signs of lung damage, if I control for that in my model, it's going to result in me misunderstanding the causal relationship between smoking and lung cancer. So in this case, I know that's a mediator, so I'm not going to touch that. I'm not going to control for that. You want to always control for confounders, don't control for mediators or colliders. And those are the three relationships, really. I presented really idealized examples of these, but in reality, is really complicated. It looks like this. So I guess I would say be brave. Take the variables you think are most important from a causal perspective, like when you get a data set, and just use domain knowledge and try to understand, like, how could this cause this in theory, or like what do these relationships look like, and bring in domain experts. Yeah, so this is usually when we do the notebook exercises, but maybe I can just sort of scroll through it. And down the road, after the session, if you're interested, you can play with it yourself. Is that clear? Is that a good font size in the back? Yeah.
Can I ask a question back to the previous
Yeah,
slide?
yeah, for sure. Yeah.
You had economic disadvantage.
Oh, yeah.
Being a causal factor, and I was wondering if it's not a collider or a mediator.
It could be. It could be. In this situation, we would want to whiteboard it, basically. Like you and I would talk through what are the reasons why you think it's a collider. Maybe this graph here is misspecified. It totally could be. And we could definitely have a conversation about that. We want to bring in research, domain experts, and just sort of talk through it, probably. Yeah. Yeah. Yeah.
Is there any way to learn causal tags from data? Or is that
Yes. This is maybe a controversial point, but I try to avoid it at all costs, honestly. It's
so like if there were like a genuine uncertainty, say in this example, and you couldn't come to some agreement.
Yeah. So it's called structure learning. You take an observational data set. Well, it doesn't have to. It could be the result of like an experiment too. But you take some data set, and it tries to learn the arrows and the direction of the arrows, applying basic rules. If two arrows are pointing this way, and I control for this thing vanishes. What does that tell me about the arrows? It's a really hard problem. It is, in terms of like computation and memory, it's super exponential. It is worse than exponential. I found like there are 10 algorithms for it, and I'll apply all 10 to a data set and get completely different results each time. So I don't know how to interpret that.
And I wonder if it's the case that even if you did that, you're sort of putting the cart in front of the horse, because then if you want to then use your DAG to empower like what you can tell from your data, like your data's already said what the DAG is. So I guess it kind of is nice to have.
That's an interesting point. Yeah.
The DAG.
It's almost like circular in a way, like using the data to make the DAG to inform how the data works or something. Right. Yeah, I hear you. Yeah, I don't know. I know some folks that do use structure learning. Their approach is learn a structure from the data, take a closer look at it once it's been learned, and sort of pick out associations for sure are BS, and then sort of like fine tune it with your domain knowledge. So I guess people do that. It's just it troubles me, I guess, personally. That's just a personal problem, maybe. Yeah. Okay.
Can I ask another question?
Yeah.
Yeah, just wondering if there's a way to design experiments in like a technological setup to learn a causal tag if you don't know it a priori?
Yes. Yeah, there are definitely approaches for that. I haven't used them, but there are definitely, I've read papers in the last few years where they'll recommend interventions at just the right point to kind of elucidate the structure at this part here, which is a little bit unknown. It's like targeted intervention work. I just don't know much about that stuff, but it exists, yeah. It's probably really helpful, yeah. Okay, is the text big enough here?
Maybe a little bigger.
A little bigger? Okay. How about, let me, I wish I could like, all right, dumb question. How do I hide this side menu? Is there a way to like, oh, boom, okay, sorry. Okay, cool. So the point of this notebook was to basically engineer some data to represent those 3 different relationships we just looked at, and so you can kind of play with it yourself. So the first one, I'm looking at the teacher version, but feel free to play around with the attendee version too, is classic confounding. So I took smoking, coffee, and lung cancer, and it allows you to essentially structure this relationship. It looks exactly like this. Wait, sorry. It's this sort of relationship here where we're considering coffee as being an intervention, like, or our ability to act on that. Maybe we could restrict coffee consumption and it would help lung cancer, maybe. But we have the smoking confounder and we have to control for it somehow. So we use this package that allows you to specify the graph and then generate random samples that fit into that graph or use that graph in the data generating process. And so we come up with a data set where, for certain convenience reasons, coffee is a continuous variable and lung cancer is also continuous. There's just a sort of a convenience reason for that. You'll see in a second. And smoking is binary. So we want to calculate just basic statistical correlations here, Pearson correlations, right, between variables. I see that coffee and lung cancer, the Pearson relationship between these is actually it's moderately strong maybe. 0.5, it's moderately strong correlation there actually. It ranges between -1 and +1. So moderately strong positive correlation between coffee and lung cancer, that doesn't seem right. So I should be skeptical if I get this observational data set and say, well, I also have smoking. I know smoking is a known confounder. And so essentially, I'll just scroll down here. If I restrict the data set so it's only among non-smokers, I take out the variability of smoking. I condition on that. What happens is I now find that there is no relationship at all between coffee and lung cancer. So I've controlled for the confounder. The confounder was inducing a positive relationship between coffee and lung cancer. I control for the confounder. Now I find there's nothing between coffee and lung cancer, which is expected. I wouldn't think there'd be any causal or relationship between these in reality. So that's what it is, basically. In this notebook, you go over a collider too. We do the same basic thing. In this example, it's, what is it? A mother's genetic risk of diabetes, household income in your childhood, and a mother's diabetes. So the idea being here, mother's genetic risk of diabetes and household income both cause mother's diabetes risk. If you have a high genetic propensity for diabetes, you're causally, expected to have diabetes. If you grew up in a low-income neighborhood or socioeconomic environment, it's well known that there's a causal relationship to onset of diabetes there too. It's just classic epidemiology. So we have this mediator relationship that looks sort of like this, with like 2 things causing the collider. Remember, I don't ever want to control for the collider. We're going to see what happens when I do. Initially, I find, get my observational data set. There is essentially no relationship between mom's genetic risk of diabetes and household income. In this case here, I find no relationship between these 2 things. If I control for the collider by doing this, I now find there's like a weak correlation there that shouldn't exist. So I've just induced bias by collider bias. And then finally, this mediation example is identical to this here. So smoking causes sort of precancerous clinical damage in the lungs, which in turn causes lung cancer. Is there a correlation between those outside two, the smoking and lung cancer? Let's see. I generate my data set. Yeah, there's a moderately strong one, which makes sense, right? Smoking, lung cancer, everything that gym teachers told you for all those years, da-da-da. I control for the mediator. I control for this middle piece here. I hold it constant. I break this pathway between these two things, and now there is no association between smoking and lung cancer at all, which is not great. Any questions about that? I know it's kind of hard to like scroll through notebooks. You need to sort of play with them to understand what's going on with them. But high level, does that make sense, what we're doing here? Okay, cool. All right, cool. So yeah, again, repeated this a bunch of times, but you want to control for confounders. You don't want to control for mediators and colliders. Super controversial point here, actually. Let me magnify this. But one that I stand by. We were always taught that when you're doing machine learning, use variable importance metrics to understand what's going on with your model. It's interpretable, and it will give you a sense of what's going on in the sort of real world behind the model. You can tell a story from it. That is actually not correct. I would argue that, SHAP, permutation importance, all these things we use to sort of understand the importance of variables in models only tell you about their contribution to the predictions of the model and how useful they are. So, we can get in a situation where you have this result and you could say, cool, maybe I'm looking at 150 features here, but only these are useful. I'm not going to use the rest because it simplifies my pipeline and makes my life easier. Like that's a use case for variable importance metrics, right? But they do in no way tell you, okay, the title is this high, so it's causally really important to predicting something. It doesn't tell you the actual causal story around things. Using the example from before of ice cream and violent crime in the city, ice cream would be super high importance in this chart here if you threw it into a model, which is, that doesn't tell you anything causally, honestly. So, so to determine causality, you need a combination of domain knowledge and causal inference methods. That's the only way you can really get at it. So just, keep that in mind. I think these plots and methods are super important, just not for, go ahead.
So surname is a collider, and you condition for it. So you take, you take these and you say, I'm going to get rid of the bottom 5.
Surname?
My model easier.
Oh, surname length. Okay.
Yeah,
Yeah.
sorry. Or let's say random or anything else.
Got it.
So if that's a collider, then I'd be biasing my model then.
Yeah, you wouldn't want to include these things in a model for sure.
No,
Yeah.
you would. I guess if it's a collider, you don't want to necessarily take them out. I guess you're not taking out all the rows. You're just taking out that data.
So if you control for the collider in your model,
Yeah.
it's going to result in like a spurious relationship between your treatment and outcome. So you'd want to keep it out. Yeah. Ideally, okay. I guess this isn't really supposed to represent like a causal model per se, but just sort of a general ML sort of approach to things. Like I use a random forest model. In sklearn, I can really easily get the variable importance, and you get something like this. I'm just saying that the practice of reading this and being able to tell people a story about what causes what is not a good one, I would argue. Yeah, that's all.
But as far as causality,
Yeah.
you have to afford the income to diabetes. There's a possibility that there's a confounder in between those two that you just don't know about.
Yeah, that is absolutely right. Yeah. Oftentimes when you're kind of whiteboarding this and drawing out the relationships, you'll find that, okay, I've drawn a line between this and this, but there's actually a whole bunch of things going on there. And hopefully you have data on those things so you can sort of control for them and model on them. If you don't, then things get a little tricky and you have to sort of, do deeper digging into whether or not your problem is solvable with what you have, or maybe you need another solution or something like that. So it's a big problem, yeah, for sure. Yeah. Okay. Does everyone have the slides open right now? Or is it, okay. This is, I don't know, like a group activity, I guess, but there are 4 big assumptions to causal inference. I mean, it's not magic. There's no free lunch. It's a useful thing, and it will help you determine causality, but certain conditions have to be met. The first of which is, causes always occur before effects. That's, just basic, that's how the world works. And so whatever treatment variable you're considering, in the case of the New York Times talk from the first day, that would be sort of, how do we ratchet this thing left and right? That's the intervention we can do. Your data, I mean, the way you sort of have your data set constructed, that has to have occurred before the outcome, if that makes sense. If it's flipped around, then you're not really telling a true causal story from this. It's something else. It's just, I don't know what it would be. There's something called the stable unit treatment value assumption, which is just, you can simplify that to just the treatment of an individual doesn't affect the outcomes of other individuals. So in cases when you're doing like social media causal type associations, it gets really tricky here, unless you can actually verify that these things are isolated and sort of not affecting the outcomes of others. Positivity is a way of saying, essentially, you have enough data so that within each sort of substrata of confounders you're controlling for, you have enough data there. So if I only have like 100 observations and I want to control for like 50 confounding variables, you're going to violate that assumption big time. I mean, there won't be enough variability there for the model to learn what's going on within each of like the sort of substrata of confounders. And then ignorability, which is probably the biggest one, and you just raised that actually in the back, which is you have to account for all major confounding variables. And if you don't do that, it's unfortunate, but your results will not be trustworthy. I mean, usually that's the one that will sink you in practice. Just, you don't have what you need to control for things, unfortunately. Okay, so if you can keep that slide open, you can use it for this next few slides here. So example 1, I'm wondering if you could try to guess or just say out loud what violation is occurring here of these assumptions. It can be 1, 2, 3, or 4 of the assumptions, or whatever, or any combination. I want to understand whether frequent emails to customers might impact customer satisfaction. That makes sense. I have survey data with customer self-reported satisfaction from a year ago, and I use this past month's number of emails for each customer as a proxy for how often we email them generally. So, what was that? Temporality, exactly. Okay, so I have, I've switched around the sort of ordering, the temporal ordering of these things. The cause has to occur before, the effect. The cause has to occur before the effect, right? Okay, example 2. I want to see the causal impact of a neighborhood's cleanliness on crime rates, controlling for 20 known confounders. I pull up an academic data set with data on 40 unique neighborhoods or districts, and the unit of analysis in my analysis is a neighborhood, so I essentially have 40 rows of data. I want to control for 20 confounders. So it's like 40 rows, 20 columns. What do you think?
Positivity.
Yeah, positivity, yeah. There's no way I can have enough variability of treatment and outcome with that few observations and that many columns. It's just, there's going to be a lot of sparsity sort of in the different combinations of confounding variables there. Okay, third one. I want to see how releasing a new in-app multiplayer game through my social media app impacts user engagement. I only want to give it to some test users initially. With this multiplayer game, you can play with anyone on the app. And in this situation, it turns out test users can invite non-test users in to play too. So what do you think about that? Yeah, exactly. Second one here. And then Finally, we're curious how a job training program can impact a person's income 3 years in the future. Unfortunately, we don't have a lot of data on the participants, so we're only really going to control for age in this analysis. So it's just, was I in this program, yes or no, age, and income in the future? What do you think? Maybe I don't have enough variables there to control for. There's a lot going on, so ignorability, yeah. So you would be advised in this case not to do causal inference analysis on this. Just, I don't know. Okay, how are we doing for time? Okay, so I want to get practical now. This is stuff that you can actually walk away with and start using immediately, as long as you sort of think through, is it usable in this case? There's a technique called S-learning or g-computation, depends what domain you're in. Epidemiology, we call it g-computation. Econometricians call it S-learning. If you're in industry, you can call it whatever you want, I guess. The way it works is it's a way of using a model to control for confounding variables to assess the impact of a treatment on an outcome. So this is a really useful thing. This will answer the question of, I have some intervention, and I want to see what it does on my outcome, controlling for a bunch of things that are sort of nuisance variables, confounders, right? So, and it's very simple too. It's very easy and quick. You can implement it within like 10 to 20 lines of code. It's great. So let's say you have a data set like this, a very typical data frame. You have some set of covariates that we know are likely confounders through our domain knowledge and sort of understanding of the field. I have some treatment that's binary, and I have some outcome. And the way it works is I train a model. Any sort of model will work. Something from sklearn, it could be as simple as logistic regression. It doesn't really matter, or regression in this case. I train a model to predict the outcome from all the covariates and the treatment. So I take covar1, covar2, and treatment as my predictors, and I predict the outcome. Pretty simple so far, right? I then have this trained model, and what I do is I'm going to run the data that I trained through that model to get the predictions. But before I do that, I'm going to force everyone in the data set to receive treatment. So before, some people didn't, some people did. In the New York Times talk and the first day here, some people, through like prior experiments and such, some people got a number of articles they were able to read, 50, 20, and some people only got 5. There's some variability there. But what I do here is I force everyone to receive the treatment. So in some cases, this is the counterfactual, right? Like the IDs 3 and 4, these people actually didn't get the treatment in real life. But I'm exploring the counterfactual there. So I force everyone to get the treatment, and I get the predictions. These are the predictions, right, from the model. I then force everyone to not receive treatment, and I run it through the model again. And I collect the outcome from that. And so I don't know why these last 2 column names aren't showing up, but that's supposed to be with treatment outcome, and this is supposed to be without treatment outcome. And then what I do is I simply calculate the difference between those 2 predicted columns, and I average the effect across the whole data set, if that makes sense. Did that make sense? Did I skip over something? Didn't? Okay, so it makes sense, right? And what this 3.1 is essentially the conditional average treatment effect of that treatment on the outcome, controlling for those 2 covariates, which are confounders. And that's really all you have to do. There's a number of ways you can look at this. You can do this in the overall population, the entire data set, and that's called the just conditional average treatment effect. If you want to look at just the people that actually receive treatment in real life, that's the conditional average treatment effect among the treated. And you can look at it in any subsegment you want to. You can even get individual treatment effects. I can say, what's the effect for individual 1? It was 4, which is really cool. I can guess, like your particular, the impact of the treatment on just you, controlling for these attributes that you have. So that's a powerful thing and relatively simple too. Again, so definitely encourage you on your own time to kind of take a look at, let me pull this up. This notebook, which goes into g-computation or S-learning. In case you want to know, this is implemented in Causal ML, the Python package, so you can go right to that if you want to use it out of the box. It's there, it's easy to use, simple API. But it's also really simple to do this yourself. So in this case here, there's a classic kind of canonical causal inference data set called the Lalonde data set, or Lalonde data set, I'm not sure. And it is a job training program type data set. So you have some attributes of people, some socioeconomic covariates that we want to control for. You have earnings. I believe this is the outcome variable in this data set typically. And then there's an indicator variable here, 1 or 0, for whether or not they were part of this job training program. And we want to see if that has an impact on income in the future. So data set looks like this. You know, I can do some basic manipulation here, some scaling and such. Using sklearn, I fit a very simple linear regression model, which I think most people are probably familiar with, that API for that. And then we do what I mentioned before, which is essentially, copy our data set and then now force everyone to receive the treatment. So now, in this data set here, everyone is a 1 in this column. By sheer luck here, in these 5 observations here, everyone was a 1, but there are some zeros here too. So I do that. I get the predictions from the model. I get the mean prediction. The mean outcome predicted is this in terms of dollars. And now I force everyone to not receive the treatment, not to have attended the program, make the predictions, and I get this number here. And this delta between this and this is your treatment effect, which is this. So we can say, controlling for those covariates that we showed you earlier, the treatment effect is estimated to be a little under $17,000.
Does the treatment effect change depending on the model you pick?
Yes, yeah, that estimate can change for sure, yeah. I mean, the best guidance I've sort of gathered from people is you want your trained model to be as balanced and accurate as possible. And so, I don't think there's a problem with going with like boosted trees or whatever, or something, or gradient boosting or something, yeah. Yeah, but it will change. If we tried a different model here, it might be slightly different. You open a whole can of worms, actually. I mean, we can sort of like do this a number of ways, but you get into an issue of like multiple testing, So there are ways to get p-values associated with this and like significance. And if I were to try a bunch of different things and sort of, some are positive or significant, some are not, there are issues with that. So I typically just, early on in the process, try to train a model which is fairly predictive, fairly balanced, and stick with it. But yeah, you can. Yeah.
Do you interpret the coefficients of each of these covariates somehow to see, like just to see if one of the confounding variables contributed the most?
Oh, interesting. So, I mean, we did a lot of that, like in epidemiology and econometrics. So they use a lot of like linear models and things because you can get those coefficients and they have actual meaning. So people do that. In the case, I tend to use like gradient boosting these days for this sort of problem, and it's I don't think you can in that case really, but yeah, people take linear models all the time and interpret that causally. Yeah.
Thanks.
Assuming it's specified the right way, the model. Yeah. Yeah. Oh. I can try repeating it for you too if you.
That's fine, that's easier.
Okay. Yeah, sure.
So some of those variables could be colliders that you're conditioning for.
They could be.
But you're just taking them all in essence, you're
In this
controlling-
scenario here,
You're conditioning for everything that you're not modifying.
in this scenario here, let's say I've thought about it already, and I've sort of whiteboarded this with people, and my understanding of these are that they are confounders, not colliders. if we did sort of say, you know what, I think this particular variable is probably a collider, or maybe we're unsure, you wouldn't want to include it. Yeah.
In the example, you used the linear regression.
Yeah.
So in that case, if you looked at the coefficient of the treatment effect, you would get the same result, I think, than this approach. Or
This is true. That's true. Yeah. The only advantage I would say to this sort of approach is that you can use really powerful machine learning, and in theory, you could. I guess I don't know why you would, but it's tabular data. You could use a deep learning model to like power your g-computation, and higher predictive performance is a good thing in this case. Like it will result in better estimation of the treatment effect. But yeah, if it's a linear model, for sure, you could just look at the coefficient of that treatment variable, and that's going to sort of have controlled for the other things. Yeah.
and compared to other methods like propensity score matching, or how would the G factor compare?
Yeah. There's a really good paper out. It's in Nature, and I think they compare propensity score matching is another approach for doing this, essentially. It compares this to that to another approach under different conditions, and it depends a bit. Yeah, there's certain conditions when one is better than the other, but I think if you're getting started, this is a decent one to get started with. And it's easy to understand, and you can sort of, people are familiar with the sklearn API, so they can jump into it. But if you're interested in this stuff, definitely explore propensity score matching too. It's another way of doing it. Essentially, you match, in theory, you would match individuals that received and didn't receive treatment to each other based on how similar they are. So yeah, it's another approach too.
Thank you.
Yeah. Okay. Let's see here. So we went over that. I'm almost done, I think. But yeah, so for those that are interested, you might say, well, what if your treatment variable is not binary? Up to this point, it's only been 1 or 0. And there are ways for doing that too. Maybe you want to model price or waiting time or how much lead, how many micrograms of lead or something is in your blood. And so, you might get a data set like this, like there are different levels of treatment values here in our observational data, right? And different outcome values associated with them. And so, traditionally when we see a plot like this, we draw a line through it, right? Like the line of best fit. Or we, apply some approach to like kind of make that line smoother. But the way we think of this in terms of like causal estimation is different. What's going on here is actually kind of a missing data problem in a sense. Each of these points, that top point there, that whole path that's of dotted lines there represents the sort of person's individual true, how do I put this, like effect you would see, or like outcome you would see if they received that treatment at that point. So at this point here, we've observed that for this individual, if this is an individual, at this treatment value effect, they have this outcome. In an alternative universe, like the universe we can't access, if they had this level of treatment, we would see this outcome. So this is all missing data. The dots represent the data we know. And so generating a causal curve is a way of sort of estimating that true hypothetical causal relationship. So it's different than this one, right? This is the curve that fits with the points we see. What we really want to estimate if we have a continuous treatment variable is this, actually. This is sort of the underlying true one that we can't observe. Most of these points here are counterfactuals, right? Because we didn't see, it's all missing data or data we don't have. And so that's what you want to do with this approach. Yeah.
Why would it go, I'm just trying to intuit.
Yeah.
Why would it go up at the end of more treatment?
Yeah, I don't know. I just made it up, yeah.
Oh, okay.
Oh yeah. It's I didn't have anything in mind. I just wanted to kind of like show like, it could be some crazy effect. It sometimes happens.
Okay.
Yeah. Yeah.
Something like that.
What's that?
Too much chemo.
Yeah, maybe there's some sort of nonlinear effect that yeah, or some plateauing effect or something like that. But it'll appear different than this, what you observe only, yeah. So, we'll skip that. It's, on your own time, definitely check out this, this notebook here. It goes into how to generate causal curves. You can look into these libraries out there that do this for you and sort of the theory behind it. I don't want to overwhelm folks with the theory at this point, but it's, it's definitely very doable. In this notebook here, we take a really large public data set, the NHANES data set. It's put out by the CDC. It's a great data set, tens of thousands of people in it. And yeah, we have all these sort of, let's assume it for the purposes of this exercise, they're all known confounders. But we definitely want to have that conversation and think through that if it's a data set that we don't know very well. And the treatment of interest here is lead in your blood. We want to see if there's some causal effect to decreasing lead in your blood, whether that relates to cognitive scores in children. So if a child has less lead in their blood, do they perform better on math, reading, block and digit test? I think block and digit are like memory and spatial awareness test or something like that. So it's an important question. I mean, there's a lot of lead exposure even in New York City in some neighborhoods, and if we were to enact some policy to change that and sort of shift the curve, that might have a really great effect on the city and sort of educational outcomes, which is awesome. And so that's what you explore here in this notebook. Essentially, you get this data set, you look at the distribution of blood lead, it looks like this in this population of children. So it's skewed, as you might expect. Here, the distribution of scaled test scores. So here's the math scores, reading, block test, digit test. And now we want to do causal inference to see if there's a causal relationship and what that relationship looks like between lead exposure and these test results. And so you implement, you use this package called Causal Curve to do that. Where is it here? There we go. Okay, these are the causal curves. So what these represent, in this case here, let's take reading, for example. Dark line is the line that's estimated. This is the 95% confidence interval. What it's saying is if we had a population of children with, and the x-axis here represents blood lead, that we're at 4, is it micrograms per DL? 4 units of lead exposure. And we, reduced it to 2, this delta here is what you'd expect to see causally in terms of an improvement in test scores. So whatever the delta is between here and here, it goes up slightly. That's the estimated impact. And it's kind of nice in a way, because you can sort of visualize this thing and see any nonlinearities and see what that causal curve looks like if you have continuous treatment variables to work with, at least. So yeah, it's a pretty powerful thing. I'm going to shamelessly plug this. So I put this package together. This is my sort of COVID project in 2020. There's also this option here of understanding mediation effects. So to put it to you this way, people have sort of proposed that the relationship between lead exposure and bad educational outcomes is partly mediated by income. Sort of lower SES or socioeconomic status. And so what you can do here is answer that question in essence. You can say, as I sort of alter the level of poverty in this data set, what proportion of this relationship between the sort of positive relationship between lead exposure and test scores is mediated by this income. And you see actually it's not trivial. It's about 20% of it. So kind of an interesting outcome there to explore. So yeah, I think we're almost done. A few slides left. And so I would suggest, if you're leaving this confused, I'm sorry. I can talk to you after the talk. I hope to resolve that. But here's a simple sort of flow chart to help you on your early steps on causal inference. So if you have a treatment variable that is binary, nominal, ordinal perhaps. I recommend going down the left side of this flowchart here. Employ g-computation or s-learning to do that. That was the second notebook we looked at. If you have a continuous treatment variable, I'd recommend going down the right path here. Use the causal curve package to do that. And depending on what your outcome is that you're trying to sort of work with, continuous or binary, these four nodes on the bottom tell you which models to use or how to approach that. So, so yeah, I guess like just parting suggestions. Again, like make sure you have a pretty healthy amount of domain knowledge before you do this work. Definitely not something you want to just throw numbers in. Yep.
How do you mentioned it many times, I work in industry,
Yeah.
and how do you define domain knowledge? It just in my world, domain knowledge almost certainly would introduce bias. So how do you
Domain knowledge would almost certainly, what's that?
introduce bias?
Introduce bias? Oh, interesting. What industry are you in? I'm just curious.
Like the Internet of Things, we collect a lot of sensor data.
Oh,
and
wow.
causally
Interesting.
we try to determine if.
Yeah.
Thank you. A question we might answer is, well, does the machine that a person runs, does the person running a machine impact the speed of the process?
Mm.
And the domain knowledge would be, say, the management of that facility,
Yeah.
whom would almost certainly tell you, yes, it does. But it's an intuition. It's again, I'm kind of struggling with how you define domain knowledge because, again, in my world, that can be very tricky.
Tell me if I'm off base here. Is this almost a case of like bad domain knowledge? Like the knowledge you're getting about this domain is like bad, or like or like
it's highly biased. That
Okay.
if I see somebody working very hard, I assume
Yeah.
that person's productive. That's biased. It's not a.
Yeah. That's tricky.
Or say in academia,
I don't know.
how is
Hopefully
that,
you'd have access to some sort of trustworthy understanding of some process that's going on. It's hard. I mean, in academia, at least when I did this stuff, there's just reams of journal articles out there to rely on. You can sort of construct the DAG from what you learned from articles. I think this is causing this and that's causing that. I guess it gets trickier in some industry scenarios where, yeah, like you said, I don't know. I don't have an easy answer for that. Yeah. That's an interesting one. I'll have to think about that.
in a sense, we try to introduce a domain knowledge, to deploy the domain knowledge ourselves,
Yeah.
trying to be as data-driven as we can.
Yeah.
That, on the other hand, we kind of run up against the boundary of our own domain knowledge, and
Yeah.
it's really trying to fit in the gap. And I was just curious because, again, you've mentioned it several times. And
Yeah.
thank you.
That's a tricky one. Yeah, thanks. I'll have to think about that. Yeah. Yeah, so just some suggestions here. One thing to keep in mind is with these approaches, you can definitely calculate p-values and statistical significance, but you want to avoid scenarios where you sort of game the thing and test it multiple times in different subsets. Like you will definitely, if you're looking for a good story and you try different subsets, you will definitely find a good story, but it may not be the true one. I know some buddies in the data science industry that work under sales teams, which seems really tough. And they're in these situations quite a bit. So yeah, it's tough. And then I love this article by the smart folks at Stitch Fix. They wrote some things about roughly estimating how much of the time business ideas are actually work out or are true or work out. And most business or research ideas will fail, unfortunately. So definitely approach your results with some skepticism, but try to be open to the fact that maybe what everyone considers to be a brilliant idea doesn't work for some reason or another. So that is it. Yeah. Any questions?
Thanks for the talk again. So I know you mentioned about multiple testing, and
Yeah.
there are often times we want to measure the effectiveness of treatment group within subgroups, like, say
Yeah, that's
whether
true.
it worked
That's true.
for a particular state or. So I was wondering, in those cases, do we have that variable as a covariate in the model that we are building to, like, for the conditional average treatment effect, or do we just train two different models for each of the subgroups and
Oh, interesting.
yeah.
I don't know if I mean, I guess the approach I would take is I would train one overall model and then use that to explore subpopulations. But definitely if I'm testing a lot of different subpopulations and I'm calculating p-values from these things, I try to account for that. There's a number of corrections you can do to sort of prevent false positives. So, yeah.
Thank you.
Yeah, sure.
So I was hoping that there would be a statistical test that would differentiate between correlation and causality. What
That would be
my
awesome.
takeaway from this is that maybe there's not, right? So
Yeah.
the ice cream example you gave at the beginning about summer and whatever is
Yeah.
also used, I think, in textbooks for
Yeah.
hidden Markov chains,
Yep.
right? That there's hidden things that. So, I mean, my takeaway from this is you really have to apply domain knowledge, and even then there may be things you're not observing or not
Yeah.
thinking about that can make correlation appear causal.
Yeah.
Is that
Yeah,
correct?
for my money, this is much harder than classic ML and predictions. I mean, in that case, I have a training set, I have a test set, I can toss stuff in, and I can prove over time that it's predicting well, and I can sleep well at night, basically. But with this, there's like a bit of art involved. There's a bit of like possibly questionable domain knowledge, as this gentleman suggested, yeah, it's a little fuzzy. I don't know. I guess that's sort of that's what you have to pay for sort of trying to get at a causal claim that you can't do with an experiment. Yeah, yeah. Sorry though.
No, thank you. That's a good takeaway.
Yeah.
I've been wondering about this for a long time.
Yeah, yeah. That would be great. If there was. Yeah.
What I'm hearing is there really is no exact.
Yeah.
Okay, this is correlation, this is causality.
Yeah. I think the folks that that the proponents of structure learning, like the folks that, there's a group of folks out there that are like, we have data sets and we can, through sheer computation, we can try to figure this out. And I can try to sort of really understand causality. They may have a different take on that, but for me, that's not the case. Yeah, it's thinking through what's going on and then combining that with empirical, analysis. Yeah. So.
Because just taking this graph,
Yeah.
right, I could think in my thesis that socioeconomic disadvantage leads to higher rates of lung cancer.
Yeah.
But I might have missed one of these other bubbles.
Yeah. 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 In epidemiology, there have probably been like 300 plus papers written on the relationships between socioeconomic status, depression, and metabolic disorders. And it's like only after those 300 papers is there a review article which says we think it looks like this, like these are the structures. It's really hard, I don't know. So you just take your best stab at it and invite a lot of people and whiteboard it, Yeah.
Thank you.
Yeah, sure.
Yeah, thanks for a really nice talk. I have two questions. First is, in the case where you showed the graph of outcome versus treatment, where treatment is continuous, and then the red was kind of away from the fit to the black points.
Yes.
Would that still be the case if the treatment is randomized, or are you referring to this particular case when the treatment is observed?
Yeah. I think it would work in your case, I imagine. Yeah, if you get data from the results of A/B test. Yeah.
Okay.
Yeah. I guess though, if you have run 5 prior A/B tests and you have sort of here's treatment value 1, 2, 3, maybe then this wouldn't be the right approach, because you could make that binary, or sort of you could handle that without this sort of setting. Yeah.
And one more question also related to the correlation versus causation comment. From your perspective, do you think that randomization is like still the gold standard for distinguishing correlation and causation? So if you see two variables correlated, you run a randomized controlled trial.
Yeah.
That is what answers causation.
I think it's the best tool we have. It by randomizing treatment, you essentially break all confounding, because treatment status there's no way it can be causal sort of associated with any possible confounder, right? Because it's random. So yeah, it's the best thing I know of. I don't know.
Thank you.
Yeah.
Hey,
Yeah.
sorry.
Oh,
Is there anything special to say if you're working in a Bayesian framework? Is it basically the same? You just do your g-computation, you get your posterior predictive based on that, or is there anything different or special?
I guess not. I mean, yeah, probably not. You could code it up very similar, I imagine, and you just encode in whatever priors you have, I guess, and just let it roll. Yeah. Yeah, I know someone that implemented g-computation with PyMC3 a few months ago. And they got a nice distribution at the end of like the treatment effect is like, you know, whatever, yeah, so.
And what was the result about the vitamin D and COVID? Did that? I forget if you actually said, but.
Oh, sorry, the vitamin D and COVID? Yeah. I don't even know, actually.
You don't know?
I'm kind of curious. Let's. Oh, there you go. Yeah.
Classic epidemiology.
Yeah, interesting. Okay. Huh.
You had mentioned. Well.
Oh, is that one not working?
Oh. Better? Okay, there we go.
Yeah.
You had mentioned that there are strategies for kind of testing for mediation. And I remember like 15 years ago in the behavioral sciences, there was this whole series of regressions you'd run and subtract coefficients from each other. What's the current thinking on those strategies?
So there is a test for mediation that was proposed a long time ago. And I think I might have even used that in grad school early on.
I'm hoping we've gotten better.
Yeah.
I know I
So
did.
my understanding was it was really crude. Like you essentially get a correlation not controlling for the mediator, and then get a correlation controlling for it, and then it looks at that delta and determines whether it's significant. And that's like, I guess that proves mediation, I guess. Yeah, I don't know.
Have anything better?
I don't know anything better, really. Yeah, I'm not sure. That'd be really cool, though, if that worked. And you could really figure a lot of things out. Yeah.
I'll just say with like mediation and like survey data, there's a lot being done on the
Oh, really?
psychology space. You can get a whole book and there's a lot done on the psychology space. It's too quick for some reason. The name escapes me. I'll look it for you in like 30 seconds and have it to you. But he has a SAS macro, he has a stata macro, and that's all that he does is teach mediation with called a process variable.
Is it like a test for mediation, or?
Yeah, so you can test for that variable if it's a mediation, if there's moderated mediation, and there's like 60 odd models that you can try to.
Oh, that's cool.
Try to put through it, and it's like any statistical test. I think the problem that I have with it is that you can kind of find whatever you want. It's like, yes, this mediates. Now we can publish. So rather than more stringent tests of of like SEM or more traditional things. So
got it.
So for g-computation, you just want to make sure to take out the colliders and the mediators out of the. Now, can you leave everything else in, assuming that they're confounders? I mean, is that going to make a difference, or?
Yeah, you'd want to include just the confounders.
Oh, you don't. So something that's just neutral, you don't want to. You want to remove.
I mean, I guess. One second, let me pull this up here. So I guess like what you're talking about is something like this maybe? Where is it? Okay, so like this one here is completely unrelated to everything else, but it does happen to relate to lung cancer. Are you sort of asking like if I include this in the model, will it throw anything off?
I mean, or even if it wasn't related to lung cancer at all,
Yeah.
happen to be
I
random.
guess in a scenario where let's say like this is a very well-known structure and we all believe in it and we all trust it and it actually is true, throwing this into the g-computation model isn't going to hurt you at all. Yeah. But if it is somehow like related to something which relates to something else which causes bias, that's going to cause a problem. But if I know for a fact like it is an unrelated predictor, it's causally related to the outcome, it touches nothing else, then yeah, it doesn't hurt to throw it in, yeah. Yeah.
This is a little bit similar to the first question, but I was wondering how often do two people analyzing the same data get different results? Maybe because due to the understanding that they have.
Yeah. It can definitely happen. I'll say that much. I think the trick is to just, if you and your organization are really going to commit to doing something like this, like you can't run an A/B test, but you really want to get as close as you can to that, you have to just, gather all the stakeholders together, figure out the best structure you can, and then test it as few times as possible. Because you can game it, you can sort of find things that you want to find, yeah.
Thank you.
Yeah.
Any more questions, everybody?
Happy hour.
Okay, thank you all very much.